Hello, everyone, and welcome to another wonderful evening of See and Learn 2019. First off, thank each and every one of you guys for joining us tonight. We really appreciate your presence here with us for See and Learn. We also want to say thank you to our fans on Facebook for joining us on the live stream. We invite you guys to comment where you're watching from. And if you have any questions at the end of the show, please leave a comment and we'll try to get your questions answered for you. With that being said, we do want to thank our sponsor, Carib Trans, for making it possible that we can share this with people all around the world. We also want to give a big thank you to Hibiscus Cottage for making our expert feel at home while she's here on Saba. A big thank you to Prince Bernhard Culture Funds and the government of Saba for their generous donations and kind support. A big thank you to all of our sponsors. Without them, this wouldn't be possible. So thank each and every one of you guys. And we got a raffle going on, guys. For those of you who don't know, it is $2 per ticket. With that ticket, you guys could be winning one or any of these glorious prizes right here. We have, for our divers out there, a 2-for-1 certificate for 8 days, 7 nights aboard the Caribbean Explorer 2. It visits St. Martin, Saba, and St. Kitts. We also have a 2-night stay at Queen's Gardens Resort and Spa here on Saba. We have 2 round-trip tickets on the Dawn 2 ferry going from St. Martin to Saba, a wine gift basket from Shea Booba for our wine lovers out there, a handcrafted Triton Forge knife made by John over at Sea Saba, a 2-night stay for 2 people at Travel Inn on St. Martin. From Aquamania Adventures, we have 3 prizes, guys. The first one is a sunset sail for 2 around St. Martin. We have 2 round-trip tickets on the Edge going from St. Martin to Saba. We also have a Tango dinner cruise for 2 going around St. Martin. Last but definitely not least, guys, from our Saba local Joe Bean, we have a beautiful piece of glass art. It'll be a mermaid, a seahorse, and a turtle. So really cool prizes, guys. We're going to be drawing it on our closing night on October 27th. You do not have to be present to win. Just leave your number or an email on the ticket, and we'll let you know when you guys have won one of these prizes. So yeah, let us know if you guys want a ticket at the end of the presentation. We'll definitely get you guys in that raffle. Coming up on Saturday from tonight's expert, Sidney Lauer, we have a stargazing and constellation observation kind of hike/walk. It'll be very chill. You guys will get to know the constellations up in the sky. It'll be really amazing. It'll be from 9:30 to 10:30. Saturday is a no moon, so there should be lots of stars in the skies for you guys to enjoy. It won't be like a real hike. Sorry, she asked, how hard is the hike? It's not going to be like an intense hike. It'll be like a walk on a road. We'll find a nice spot where you guys will like look up. It's just the hike is basically for us to distinguish. It's more of a terrestrial activity and not a marine activity. So for you guys, it'll be very low key. You guys will enjoy the stars. It'll be nice. So yeah, we definitely invite you guys to join us. All right, now for the fun, guys. Tonight's expert is a galaxy expert. We have Sidney Lauer, and I'll give you guys some background information on her. Sidney Lauer is an Illinois native who is an astronomy graduate student at the University of Florida. She completed, yeah. No, another Floridan. She completed her undergraduate degree in physics at the University of Illinois, Urbana-Champaign. She is improving the ways through which we estimate the masses of real galaxies through cosmological simulations. Her work contributes to the understanding of how galaxies form and grow. Tonight, she will be presenting on a beginner's guide to galaxy formation. Please give a warm welcome to Sidney Lauer.
All right, can everyone hear me okay? Yes. All right, awesome. So first, I just want to thank all of you for being here. Thank the entire island of Saba for just existing, because this place is beautiful. Thank you to Lynn and everyone at See and Learn for inviting me, because honestly, this is the coolest thing I've ever done. This is the furthest south I've ever been. This is the closest to a mountain I've ever been. So it's definitely a week of firsts. So tonight I'm going to be talking to you guys about astronomy and specifically galaxies. Like any good science lesson should begin, we're going to begin with some history. So turns out we didn't always know that galaxies existed. That kind of sounds weird. We knew that, we existed and there were a bunch of stars in the sky, and we kind of knew the concept of our Milky Way galaxy, that white band of stars across the sky, but we didn't actually know that any other galaxies were out there, which is kind of a scary thought. So in the Roaring 20s, two scientists had a great debate. So they got into the science equivalent of a boxing ring and sparred it out. So this was between Harlow Shapley and Heber Curtis. And so they were debating what these things were that they saw in the sky. So, for hundreds of years, thousands of years, humans had looked up at the night sky and said, there's stars. There's planets. The planets move differently than the stars. We can actually watch them moving. But there were these weird fuzzy things, right? Like they weren't stars, they weren't planets. We didn't know what they were. We called them nebulae, spiral nebulae to be exact. So here's what an actual here's a newer picture. I think this was taken like in the 1860s. This is a newer picture. So they called these spiral nebulae, and they had no idea what these were. Were these things in our own galaxy? Were these things their own galaxy? What does that even mean? If they are outside the galaxy, does that mean that our galaxy is not the entire universe? How big is the universe? Some really existential crisis type stuff. So turns out Harlow Shapley won the debate because he said, there's no way these things could be outside our galaxy. That would mean the universe is way too big. That's unfathomable. We can't do that. That's crazy. And Heber Curtis was advocating for, I think these are outside the galaxy, but he lost because it sounded silly. Then a really famous guy, Edwin Hubble, came along and said, guys, actually I took the data. Turns out these are galaxies. So for the first time, we weren't alone. Metaphorically speaking, we didn't, there were other galaxies. These spiral nebulae were all of a sudden our galactic neighbors. We could look out and see that there are other galaxies hosting other stars, hosting other planets. And it's kind of crazy to think about. So that was in the late 20s that Hubble, figured out that that our galaxy was not the end all be all of the universe. So that might be kind of hard to fathom, right? Like the size of a galaxy, let alone the size of our solar system. So in astronomy, we have to think about things in a different way because things are so large, far away, huge, massive. So we come up with our own set of units. So let's just orient ourselves at the smallest scale, our solar system. So this is as small as we go. This is as small as we think. So in our solar system, you've got our sun in the middle, and there's the Earth and all the planets orbiting around, happy, we know that. So to talk about distances in the universe, we first define a unit called the astronomical unit. So the smallest distance we start is 150 million kilometers. That's the smallest scale at which we think. So the astronomical unit is just the average distance between the sun and the Earth. So the Earth is 1 AU away from the sun. So on average, the Earth is about 150 million kilometers from the sun. So Jupiter, for instance, the fifth planet from the sun, is about 5 AU, so 5 times the Earth's distance away from the sun. But even the astronomical unit isn't good enough to talk about things outside of our solar system. So if we want to talk about, I don't know, the nearest stellar neighbor, so where the nearest star to our solar system is, then you're talking about like 1 million AU, and that again is kind of hard to fathom. So we come up with a different, I forgot I wanted to do this. So I wanted to try to make this a little bit fathomable. So I Googled this. The distance between Ceiba and St. Martin is about, we'll call it 50 kilometers. So that means if you want to travel the same amount of distance between the Earth and the sun, you'll make that trip about 3 million times. Boat or plane, it doesn't matter, but about 3 million times. So that's pretty far. Maybe some of you have done that. Maybe you've traveled 1 AU. That's crazy. All right, so the next unit that we talk about is a light year. So you might have actually heard this, a light year. So it turns out a light year is not a unit of time. It's actually a unit of distance. In fact, it is the distance light travels in 1 year. So it turns out that that's about 9.5 trillion kilometers. And this kind of sounds like a funny way to measure distance, but it's actually quite useful. And it's based off the fact that the speed of light is constant. So if the speed of light is constant everywhere, it's standard. It's a standard ruler. We can use it to define a distance. So, we call it a light year, 9.5 trillion kilometers. So if we do that, turns out the nearest star to us is about 4 light years away. But then this brings up another thing to think about, which is, 4 light years, it takes light 4 years to travel from this star to us. So then you can kind of start thinking about, things further away from us, 10 light years, a star 10 light years away from us, it takes light 10 years to travel from that star to us. 1,000 light years away took that light 1,000 years to travel to us. So effectively, the further things are away from us, the longer it takes light to reach us, and the further back in time we are looking. So we'll come back to that point in a second. I'll just let that kind of settle in, that existential crisis. Again, I feel like we're going to be touching a lot on existential things, so just let me know if you need like a moment to breathe or something. All right, so we're going to zoom out again. So we left our solar system local neighborhood. So now we're talking about the entirety of the Milky Way galaxy. So this is an artist's rendition of the Milky Way galaxy. We don't actually have a picture of the Milky Way galaxy because we're inside of it. So we don't actually know what it looks like. But we can kind of guess. So this yellow dot is our sun. Well, solar neighborhood, about 200 light years in diameter. And it turns out our solar system is about 26,000 light years from the center of the Milky Way, which itself is about 100,000 light years across. So if you're standing on one side of the Milky Way looking at light from the other side, that light took 100,000 years to get to us. So that's pretty crazy. We can zoom out even further. So it turns out the Milky Way has neighbors. So there's us in the Milky Way galaxy. And there's our nearest large galactic neighbor, Andromeda Galaxy. And it's about 2 million light years away. So if you're outside, I think you should be able to see Andromeda outside at night. And if you see the little smudge, just know that that light is 2 million years old. So you're seeing Andromeda as it was 2 million years ago. So another maybe less well-known thing is that the Milky Way actually has little satellite galaxies that orbit it. So just like the moon orbits the Earth, we have little dwarf galaxies that orbit us. The most famous are probably the Large and Small Magellanic Clouds. So people who live in the southern hemisphere are very, very lucky because you can actually see these. Those of us who live in the north aren't lucky. You can't see these in the night sky. So if you are in the southern hemisphere, I encourage you to look up and try to find our little satellite buddies. We can zoom out even further, and maybe you don't want to, but we are going to. So here's the Milky Way again, and there's Andromeda. and we keep getting further and further away, and soon we kind of encompass the local galactic group, which is, all the nearest galaxies to the Milky Way, and we keep zooming out. And keep in mind that every dot is a galaxy. So we're zooming by all galaxies, and you can start to see large-scale structure form, right? Like there's a cluster of galaxies, there's a cluster, and by this point, all the dots are clusters of galaxies. So we're seeing groups of millions of galaxies. And each of those galaxies contains billions of stars, and those stars host exoplanets, and it's pretty big. So there's essentially the observable universe. So you're in there somewhere. All right. So let's back up a bit. So we're talking about galaxies. So this is a very famous picture. Does anyone want to guess what this picture is? Yeah, okay, so the Hubble telescope, yeah. So it's actually one of the Hubble deep fields. So what they did is they took Hubble telescope and stared at a non-suspecting patch of the sky. There was nothing special there. They stared at it for about 12 days and came back with this beautiful picture. So every dot in this picture is a galaxy besides a couple stars, but every dot is a galaxy. So like there's a nice spiral galaxy, there's a weird shaped galaxy, there's a yellow one, a blue one, yeah. So this picture is crazy. You can zoom so far into this picture and find smudges of galaxies that were there thriving in the universe when it was only about 800 million years old. So for reference, the universe today is about 14 billion years old. So 800 million, that's quite a young universe. But I feel like we're kind of getting ahead of ourselves. What is a galaxy, right? Like, okay, we're not alone in a galaxy, but fundamentally, what is a galaxy? So that answer is actually pretty simple. Turns out it's just a collection of stars, gas, and dust. And they're held together by something called gravity. So hopefully we're all familiar with the concept of gravity. It's what's keeping us on the Earth. It's what's keeping the Earth in orbit around the sun. And so analogously, it's what keeps all the stars, gas, and dust in orbit in the Milky Way galaxy. So that's essentially what a galaxy is. It's a bit more complex than that, obviously, but at top level, that's what a galaxy is. So galaxies come in all different shapes and forms. Even though the recipe is relatively simple, you're going to end up with some pretty diverse results. So you're going to have like spiral galaxies. You can see galaxies edge on, where you just see the disk, or you can see them face on, where you actually see the spiral arms. You can get some weird stuff going on where, what's happening there. You can get some kind of boring ones. These are called elliptical galaxies. But yeah, they come in all different shapes and sizes. Why? So it turns out to answer that, we have to answer first, how does a galaxy form? So we know what a galaxy is. Okay, well, how does it get here? So it turns out we have to go to the very beginning of everything. And so I present you with one of my favorite quotes, which is from The Restaurant at the End of the Universe by Douglas Adams. The story so far: in the beginning, the universe was created. This has made a lot of people very angry and has been widely regarded as a bad move. Yeah. So yeah, we have to go to the beginning. So in the beginning, there was an event that you might be familiar with called the Big Bang. So essentially, there was a huge explosion. All the matter and energy that is in the universe today was created. Some crazy stuff happened. And then for a while, nothing. So all that was in the universe at this moment was hydrogen and helium. It was kind of a very boring universe, an entire universe just filled with gas. But importantly, that gas started to collapse into gas clouds, and they formed the first stars. And then the gas and those first stars eventually formed the first galaxies, and then those galaxies grew, evolved, and did all kinds of stuff, and that's where we end up today. So the most important thing with galaxy formation is understanding, what happens in the very beginning. And all that is that gas comes together, forms stars, and then those stars and gas are in a disk, and that disk begins rotating, and that's how you get these spiral arms of a spiral galaxy. So, it's a very thin disk, and it's rotating. All right, so the next logical question to ask is, what happens to a galaxy once it's formed? How does it evolve? And so that actually depends on roughly two things, two categories of things. What happens to the things inside of a galaxy, and what happens to the surrounding, how is the galaxy affected by its environment? So to answer the first part, what happens to the stars? So we talked a little bit, just about this earlier. So stars form in these massive gas clouds. So the gas in this cloud collapses even further and forms stars. And then those stars themselves evolve, which is going to affect the evolution of a galaxy. So it turns out again that the properties of a star are all related. So a star's mass, when it's born, kind of determines its color and its temperature. So if a star is born very massive, it's going to tend to be blue and very hot and very large. If a star is born not massive, it's going to be born red, it's going to have a low temperature, and it's going to be very small. And so this is important because observationally we can distinguish between populations of young and old stars. So young stars are going to peak. So first off, this is a plot of a star's color. So over here, wavelength really. So over here is going to be like blue, green, and then red. And then this is just brightness essentially. So we can separate because young stars are going to tend to be very, very bright. They're always going to be brighter than anything colder than it. And they're going to peak in the blue. So young, hot stars are going to look blue to us. Conversely, the old stars, they're going to be cooler, and they're going to be in the red. They're going to peak in the red wavelengths. So an important thing also to note is that that saying, hot stars die young, that's literal. So stars that are born massive, hot, burn up all their fuel very, very quickly, and then are gone. So we know when we see a star that is blue, we know that it has to be a young star. Because, in less than 50 million years, it's going to be going away. So just statistically, if you see a star out in the sky that's blue, you know it has to be young. So with that, mass also determines, what happens late in a star's life. So if you're born massive, you're going to evolve into becoming a supergiant. So these are going to be, very, very large, like Betelgeuse type stars, which is like 1,000 times the diameter of the sun. And then they'll evolve once more and then die in a supernova explosion. So all this takes place in roughly 50 million years. But if you're born somewhere on this plot, like the sun is, you're going to evolve and just become a regular giant. And then late in life, you're going to have a sort of explosion, but it's not going to be a supernova. What happens is that the sun will shed its exterior layers of gas and become what is called a white dwarf. So not as exciting. But on the flip side, or I guess an advantage of this, is that the sun is going to live for billions of years. And if you're luckiest, if you're the lowest mass stars born, billions and billions and billions of years. So you're going to live a long time. So we know that if we're seeing, a red star, we know that it's very old. And we know that if we're seeing a blue star, we know that it's very young. So what that means in terms of a galaxy is that, okay, if you're handed a galaxy that looks like this and it's blue, you know that this is a young galaxy because it has young stars. These stars were just born. They're emitting blue light. Bingo. We know it's a young galaxy. Over here, if you're handed a star that looks like this, no blue stars in sight, you know that has to be an old galaxy. All of its blue stars died out. So, just understanding the evolution of stars allows you to understand how galaxies evolve. On the other hand, the galaxy's environment also affects its evolution. Kind of akin to, if you're growing up in a really big family with a bunch of siblings, you're all going to fight and, not get along very well, versus if you're a single child and you're there, it's going to be kind of isolated and you're not going to be affected by your non-existent siblings. So if a galaxy has a nearby neighbor or is in a galaxy cluster, there's a chance it could merge. So our Milky Way is actually going to merge with our neighboring Andromeda galaxy, I think in a couple billion years, give or take. So obviously we don't have to worry about that. But even if it were to happen tomorrow, we still wouldn't have to worry about it because, we just saw the distance scales in a galaxy are so huge that nothing is going to run into us. We do not have to worry. All right, so this is just showing this isn't the same set of galaxies in each picture, but it's roughly showing you how a merger takes place. So you have two galaxies that are close together. Their gravity attracts them. This is the first pass right here. Looks like second pass right here, and then eventual coalescence. So what this tends to do is that when these galaxies interact with each other, they kind of stir up all the contents inside that galaxy, and it disrupts the tidiness of those disk galaxies and actually turns them into something that's more spheroidal. So again, what this means is that if you're handed a galaxy that looks like this, where the stars are not in a spiral shape, they're not in a disk, that galaxy had to have gone through a merger. And for it to have gone through a merger, then it's probably pretty old. And so it turns out that galaxies, we think, emphasis on think, that galaxies start off in disk spiral shapes, and then through environmental effects, turn into a more spheroidal shape. That's a good question. How do we know? So I said emphasis on think. So that's astronomy. So there's two basic ways that we have and you can figure this out. So that's observations and theory. So astronomy is a little different, right? We don't get to go travel to a star and ask the question, what is a star made of? We don't get to send a spaceship down to the surface of a star and collect samples and use a microscope because one, we don't have a spaceship that can do that, and two, it's a star, so you'll die. You can't get on the surface of a star. So we have to do things a little bit different. Instead of microscopes, we have telescopes. So with observations, we use telescopes to observe galaxies. What this means is that astronomy is very indirect. We don't really have direct ways to understand the components of our universe. We can do even more abstract things with theory. So theory is a bit scary. So just think of theory as Albert Einstein sitting somewhere in a dark room with a reading light hunched over his desk, figuring out the equations that govern the universe. So we can use what we know about physics and what we know about astronomy already and try to make models that make predictions that we can test. So first a little bit about observations. So I said we use telescopes. And we use a lot of telescopes. And we use telescopes that might not look like a telescope. So these first two that I showed you here, this is Hubble Space Telescope again. And these are the Keck telescopes, Keck 1 and 2, on Mauna Kea in Hawaii. And these are both optical telescopes. So they operate in the visible wavelengths where we can see. So whatever these telescopes take a picture of, we can look up and see the same thing. But there's a lot more light that we can't see. So we just see, a very narrow wavelength regime, from 400 to 700 nanometers. So, blue to red light. But we can look at a much wider regime if we look at if we use different kinds of technologies, different telescopes. So these two telescopes, this is, I believe this is VLA or ALMA. Yikes, I should know that. And this operates in the radio wavelengths. And this space telescope right here is Chandra X-ray. So this is looking at X-rays. So like how we use X-rays to look at our own body, we can turn those X-ray machines, well, figuratively, to the sky and look at X-ray emission from galaxies. And so even more than that, these telescopes tell us different things. So if you're looking in the visible regime, you're going to see all the stars in the galaxy. And if you're looking in the infrared, you're going to see, dust emissions. So galaxies are full of dust, and that dust absorbs light from stars and re-radiates that in the infrared. So if you look with an infrared telescope, you're going to see dust. Radio picks up particles that are being accelerated in magnetic fields. So there's crazy stuff going on there. And then the ultraviolet and X-ray are picking up more crazy things. So X-ray picks up like black hole stuff accreting into a black hole, sends out crazy energetic particles in the X-ray and ultraviolet. So we have a lot of tools in our belt if we have telescopes that can pick out all these different wavelength regimes. So even though it's an indirect means, we have a lot of ways to figure stuff out. And so, we take pretty pictures of this galaxy in different wavelength regimes, but that's not, it is science, but it's not the actual science that we do. So what we do is we take these observations of light and turn them into properties of the galaxy. So we can use that light and relate it to, say, the mass of a galaxy. We can relate it to the color of a galaxy, the brightness of the galaxy, the velocity of the stars in the galaxy. And it turns out that a lot of these properties are correlated, and so we can start to pick out relations in the properties of these galaxies. So what that means is that, okay, now we have this established as our understanding. If we go out and measure the velocity of the stars in a galaxy, that means we have a reasonable guess for what its intrinsic brightness is. So observations isn't about just taking pretty pictures, even though that's a really good motivation to do observations. We also do a lot of data analysis with this to turn it into properties that are useful to understand the galaxy and how it changes. So on the other side of this is theory. So theory, again, is using the principles of physics and astronomy and chemistry and biology that we know, and creating models to describe the universe and testing those, making predictions from that, and testing it against observations. So this is a pretty famous plot. It's okay if you don't know it, though. When I say famous, I mean like famous in astronomy. I wouldn't expect you to know what this is. So what this is showing is radius, so distance from the center of a galaxy, and velocity. So how fast is something moving as a function of how far it is away from the center of the galaxy. So if we take what we know about gravity and things like that and make a model and make some predictions, we would expect that there to be roughly this sort of trend where, as you get further away from the center, as you get further away from all this mass, your velocity will drop off. Turns out, though, when we went to measure it, the exact opposite happened. Turned out it didn't decrease. It just kept on going. So this was very puzzling. We thought, how is it going so fast if there's not material out there to make it go that fast? So it turns out this was a very groundbreaking discovery. This is one of the, I hesitate to call it proof, evidence, I don't know, I'll call it evidence for dark matter. So I lied to you a little bit earlier when I talked about the components of a galaxy. I told you it was just stars, gas, and dust. Turns out there's a fourth thing in there, which actually takes up quite a majority of the mass of a galaxy, which is dark matter. So it turns out, I think it's probably more than 2/3 of the matter of a galaxy, we have no idea what it is. From these observations, we know there has to be more mass. We just can't see it. So we call it dark matter. So that's a huge topic in research in astronomy right now, in physics, is determining the nature of dark matter. But it just goes to show that, sometimes, we may understand, writing a model down, making predictions, and then testing those predictions. That's what science is. So theory is very important. I really like this comic because it applies to me. So turns out today, a lot of astronomers don't even use telescopes in the way that you think we probably do. So back in the olden days, like with Heber Curtis, Harlow Shapley, Edwin Hubble, you name it. They had telescopes in their backyards. They would go look up at the sky, make discoveries every night. That is very much not what astronomy is these days, for a couple of reasons. One, it's not very... we can't really afford to make telescopes in our backyard anymore. That's not an enterprise anymore, because we need to make larger and larger telescopes because we want to see further and further away. Yeah, you could have, an amateur telescope in your backyard. That's fine, but you're not really going to make discoveries with that, and that's okay. But for those who want to make discoveries, we have to build bigger and bigger telescopes. So you can't really do that by yourself anymore. So then it's going to come down to a team of engineers to build a telescope. And then they get scared because astronomers aren't engineers and they don't want you ruining their technology. So then turns out you don't even get to go to the observatory anymore. A big thing in astronomy now is that a lot of us don't even physically use a telescope anymore. We just handle the data. It also happens because it's just not practical to build things in our backyard anymore from an environmental sense. Where I'm from in the US, it's not even a big city, but you can't really see the night sky anymore. Sure, you could see a couple more stars with a telescope than with your naked eye, but you can't see, it's not going to be pitch black dark. So when lights came along and people built up cities, you can't really have telescopes in your backyard making these discoveries. So now we have to put them on remote places like mountaintops, deserts, so they're very inaccessible. But this also segues into a subset of theory, which is simulations. So that's what I do. So I work in cosmological simulations. So not only do I not use a telescope, I don't even use data from a telescope. So what I do is I use big supercomputers. That's the official authoritative term for that, a big supercomputer. And we put in our knowledge from theory and observations, theory about physics, and make simulations about really anything, about planet formation, about solar system dynamics. But my bread and butter is galaxy formation simulations. So these have gotten very sophisticated over the years. So we started out just, simulating isolated galaxies with, a couple thousand particles, up to huge simulations that are thousands of light years across, with millions of particles simulating the formation of hundreds, thousands of galaxies at once. So really, truly, we have a universe in a box that we're simulating. And so what we do with this is we put in what we know about physics and make observations of our galaxy and see if they jive with what we know already, see if they jive with existing observations. And then if they don't, we tweak some of our models, but then this allows us to understand the nitty-gritty of galaxy formation. So really, I've just given a top-level view, but a lot of what goes on in a galaxy is very complex. It's coupled. So things like star formation take place on very small scales, and we don't really quite understand it. We know the big picture, but we don't know the details. Things like black holes, how do the black holes merge? How did they grow? Where did the first black holes come from? Magnetic fields. There's a lot of things that we don't know, even about something as, quote, simple as a galaxy. So simulations allow us to understand that. So what this movie is showing, and it's a mesmerizing movie, I've watched this like time and time again. So this is from a simulation called the illustrious TNG simulation. And this is simulating a galaxy forming over time. So this is, literally moving in time. And it is accreting gas, and the brighter it is, the more gas is there. So you can see little satellite galaxies orbiting around the big, massive spiral galaxy in the center, accreting gas, forming stars, and just living its best life. So yeah, this is what I do. These are the type of pictures I get to look at. Yeah, okay, maybe they're not Hubble pictures of the Eagle Nebula, but they're my own, pictures to look at, and it's helping us understand real galaxies out there. If we can really nail down what's happening inside the simulation where we can control the conditions, then we can apply that to real-world galaxies and understand that. All right. So that actually sums, that is my presentation, so please, any questions? Yeah. Liz.
When you go to work in the morning, what is your to-do list?
All right. So when I go to work in the morning, what is my to-do list? So first thing, make coffee, turn on the computer, and then I log into the supercomputer, fire off a couple models, and then get the output from those models, make plots and plots and plots. So really my job is making pretty plots and then pondering those plots for hours and then making more plots. So it sounds a little tedious, but I promise it's fun. Yeah, good question. Yeah.
So we know stars die. Galaxies die?
Oh, good question. Yeah, so we know stars die. Do galaxies die? So they don't die in the same sense that stars do. So stars do die in kind of a rather sexy way, exploding. Galaxies kind of burn out and fizzle. So what we call a dead galaxy is a galaxy that is no longer forming stars. So like the pictures I showed you earlier, that's actually a good one. Yeah, so galaxies like this, where they're not blue, they're obviously very old, and they're spheroidal, they're not forming stars anymore, so we call those red and dead galaxies. So a galaxy is pretty much dead or quiescent when it is no longer forming stars. All it's doing is just hosting old stars and going along. Yeah. Yeah.
If the data you're looking at is millions of years old, I guess we don't really know what's currently happening now. We're not going to be around to know what's currently happening now.
Yeah, that's a good question. So if the light that we're looking at is millions of years old, how do we know what's going on today? And we don't. We're essentially looking at old information. We're looking at the universe as it was at that time that the light was emitted. So, yeah, that's a great question.
What do you hope to discover out of all your data and research that you do?
So what do we hope to discover? I think it's a bit more of what could we discover. I mean, the ideal is that we fully understand how galaxies form and how they evolve and, the nitty-gritty details of that. But I'm not... does that answer your question? Yeah. Good enough. That's when I go home. Good enough.
Is the composition of all these galaxies similar? You talked about certain gases way at the beginning.
Yeah.
But is the composition the same? And if so, hey, we've got life in ours on Earth. Is it believable that some of these other galaxies could be hosting the same kinds of planets?
Yeah, great
Maybe
question.
Similar and happening way in that other one.
Yeah, who knows? So the question was, all these other galaxies have stars and gas, and if it's the same as the gas in our galaxy, then who's to say if there aren't planets and those other galaxies hosting their own see and learn and pondering about us existing or something? Yeah, great question. So a lot of a lot of things in science happen with approximations. So actually, I love this slide. So what we do is approximate, say, you look at this galaxy and say, okay, it's a spherical cow. And so this story is that a team of scientists wanted to understand the aerodynamics of a cow. And they worked for days and days and days. And the only solution that they could come up with worked for a spherical cow with no spots. So, it doesn't really apply to what we're talking about. So we assume to some part that other galaxies have similar characteristics as our own galaxy, because why not? We don't really know any better. And of course, that's a lot of research, is figuring out if there are differences and why. So yeah, totally plausible that stars in there, definitely that stars in these galaxies have planets, plausible that those planets host life. So right now, our study of exoplanets is kind of sequestered to our own galaxy, just because we have to resolve the stars, and to be able to see the stars, and if they're too far away, all we see is the average of all the stellar light. So our understanding of exoplanets, only goes out to, only a little bit outside of our stellar neighbors. Yeah, but great question. Yeah, in the back.
Yeah, so in today's culture, with science somewhat being under attack, with uncertainty maybe, think global warming, astronomy is in itself is kind of in its infancy of technology and discovery. How do you as an astronomer defend against assumptions that a lot of what you say is faith-based according to your science versus non-believers, if you will?
Yeah, great question. So, with sometimes science being under, the question was, sometimes science comes under attack, like with global warming, fake news, whatever. Astronomy kind of treads another line, which is, okay, we're talking about the creation of the universe, creation of life, and that, might be a touchy subject for some people. How do we deal with that? So first, I guess I don't really want to dive into religion. You can believe what you want to. That's totally fine. But this is, what we've discovered, and this is what I believe. And so I will say that, and maybe I'm lucky, no one has ever come up to me and said, oh, you're wrong, you need to, save one person, you need to go and read a certain chapter of a certain book, and you'll have all the answers you need. It actually comes from a different avenue, which is conspiracy theories, which I think are maybe even a bit more dangerous. So that's what I'm talking about, is the type of stuff that gets passed around online, and the moon is a hologram and it's a conspiracy and the government is hiding, NASA isn't real, we're all spies, and we know what the government is like. There's no way we could cover that up, right? So so I think the people who maybe bring up those questions are questioning. It's totally fine to be skeptical of science. That's great. That's what science is based off of. But bad faith stuff like that, it's difficult to deal with. Yeah.
What are the theories about why the universe is speeding up?
Oh, great question. So I think you mean why it's expanding.
We've always known it was expanding.
Yeah.
We assumed it was slowing down because it was an explosion. So recently we found out, due to detection of gravitational waves recently, and et cetera, that it's speeding up. It should not be speeding up.
Yeah, great question. So the question was, how did we know? Sorry, what what are the theories about why the galaxy is accelerating its expansion? So I didn't actually touch on that. I do have that picture, I think, somewhere. It kind of doesn't matter. But essentially, the space itself expands. And we've known that for a while. We've known that since Hubble. Hubble wasn't actually the one that interpreted it that way, but he took the data. So what we know is that galaxies that are far, the further away a galaxy is from our own Milky Way, the faster it appears to be moving away from us. And so it's like, is it us? Like, why are they running away from us? But no, it's actually that the space between us is pushing them away. space itself is expanding. So it's not that the galaxies are moving away, it's that space between us is getting larger. So a new development is that expansion is actually accelerated. And again, we're touching on a thing that I kind of didn't go over, in that not only is there dark matter, but there is dark energy. So we posit that dark energy is the reason that the universe is accelerating its expansion. What is dark energy, you may ask? We say we don't know, but it's the reason why the universe is expanding. It's accelerating its expansion. So if the universe were just matter, so what we see in the dark matter and light, radiation, then the universe would end in what is colloquially called the Big Crunch, as a converse to the Big Bang. So yeah, if the Big Bang happened, then the matter and all of its gravity would eventually make everything suck back down, and I don't know, maybe it's a cycle. But turns out that's not what we observe. We observe that the expansion is actually accelerating with gravitational waves, with supernovae observations, and measuring the distances with those. So it turns out it's actually accelerating, and we say dark matter is the reason. Yeah. All right. Any more questions? All right. Well, I really enjoyed talking with you guys. Those were great questions. All right. So, okay.
Thank you, Sidney, for that mind-blowing presentation. Another round of applause, guys. All right, we have just a few more upcoming events for See and Learn 2019. On Friday, we have another presentation by coral expert Dahlia Hassel, who is here tonight. Yeah. She'll be presenting at Hideaway at 5:30 p.m. Then on Saturday is a double feature. We have two field projects. The first one is at 9 a.m. and then again at 1 p.m. at Fort Bay Harbor. Our shark expert, Chelsea Black, will be taking you on a shark dive. Then Saturday night, we have our stargazing constellation walk with Sidney Lauer, who you just had the presentation with tonight, so that should be super awesome, yes. And then Sunday for closing night, we have our shark expert giving a presentation at 5:30 p.m. at Shea Booba. So lots of cool stuff to look forward to in the next few days. Yes. I'd like to thank all of you once again for coming. This is an amazing crowd. Thank you so much. This is just awesome. Thank you, Facebook, for tuning in. We'd also like to thank all of our sponsors. Thank you, Scouts, for hosting all of us. We would invite you to stick around for drinks or dinner here at Scouts. And then, as always, we'd like to give another big round of applause to Carib Trans. Thank you for making it all possible. And with that, ladies and gentlemen, have a wonderful night.
Miami is known as an international community and the hub of trade and logistics for the Caribbean and Americas. A leader in the freight logistics industry, Carib Trans has served the Caribbean for more than 30 years, with a footprint that has grown from one island to now serving the majority, as well as Central and South America. Carib Trans is an NVOCC, a non-vessel operating common carrier, meaning it has the same responsibilities as a shipper without owning the vessels or planes. Its primary customers, individuals who ship clothing, electronics and other personal items, and occasionally cars.
Most of the stuff that they're sending is because they don't get it there. So for us to provide it on two services, air and ocean, we can give it a choice of how fast you want it. So if you want it really fast, we're going to send it by air, you're going to have it next day, sometimes even the same day.
That on-time service has been the key to Carib Trans' success, whether shipping by air or by sea. The company moves about 5,000 TEUs of freight each year, more than any NVOCC in the region. And since it joined the Saltchuk family of transportation companies a couple years ago, CaribTrans can offer customers even more shipping options.
Other NVOCCs, they depend on other shipping lines that are not part of their family. So they need to rely on whether they're going to sell or not, whether they are late or not. It doesn't happen to us because it's part of our family of companies. We control the service that we give.
Sí, buenos días, por favor, con Diana.
Quality service is what keeps customers coming back. Customers are treated like family, and when they leave to research competitors, it doesn't usually last long.
They have left and they have come back because they've said that, nobody does it better than CaribTrans. So because of that relationship.
That exceptional service includes consolidation. Customers can have freight sent here and stored for free for up to a month, then consolidated and shipped on to the islands and Americas. A perk for the region's growing small business market. Puerto Rico is an expanding market for CaribTrans, about the size of Connecticut and rich in history and culture. Puerto Rico is home to many pharmaceutical manufacturers, as well as a thriving tourism industry for which CaribTrans moves raw materials and supplies. But serving small businesses is still the company's bread and butter here in San Juan. Businesses like Caldera Café, a local coffee company. Owner Alfredo Rodriguez started growing coffee beans at his mountain farm about 20 years ago. He recently ordered a variety of new equipment for his farm and shop. He uses CaribTrans because it consolidates shipments, which cuts down on the number of times he has to pay the Puerto Rico import tax.
Not many companies want to do that. They want only big cargoes and maybe half container or full containers, but they don't want to consolidate because it's more difficult.
Turning challenges into opportunities is what CaribTrans does, and that includes helping to grow small businesses like Caldera Café by taking the hassle out of shipping.
We can be a gateway to expand their business in the Caribbean and back to the U.S. Wherever they can sell their products, we are also going to be a partner for them.
That customer dedication has made CaribTrans what it is today. Now as part of a larger family with more transportation resources, CaribTrans hopes to grow beyond its current market, offering services to additional Latin American ports and eventually Europe and Asia. But even when it becomes a global logistics company, CaribTrans wants to stay true to its roots, always providing personalized, reliable customer service and a commitment to the communities it serves.